Hello, my name is Griffin Dietz, and I'm a research scientist at Apple. Today I'll be sharing work completed during my PhD in the computer science department at Stanford University on Visual StoryCoder, a multimodal programming environment for children's creation of stories. Despite recent emphasis on computing education for all, many of our youngest learners lack the advanced literacy, numeracy, and fine motor skills needed to use most traditional programming environments or computational thinking tools. In our prior work, we addressed these challenges in StoryCoder, a voice-only smartphone application that introduced computing concepts to pre-literate and early reading children through accessible, approachable, and engaging storytelling games. While StoryCoder showed that a voice interface can be successful in delivering pedagogy, this approach can also present cognitive load and navigation challenges that can prevent users from creating more complex stories. To use a voice-only app, children need to remember everything they've done previously in order to decide what to do next. And if they want to go back or navigate elsewhere in the app, the overhead for doing so is a lot higher than it would be if they could just tap a button. Block-based interfaces, on the other hand, are the dominant paradigm in computing education today. Although they present continuous cues and reminders through a graphical interface, they can suffer from a lack of built-in instruction, which can make it hard for children to succeed if they don't have access to educator support. From these observations, we developed Visual StoryCoder, a multimodal system that blends the strengths of these approaches to overcome their respective weaknesses. In designing our multimodal Visual StoryCoder system, we also aim to resolve the most common obstacles children faced when using StoryCoder. Through a qualitative analysis of StoryCoder session data, we identified 3 additional design objectives to consider. First, confusion around instructions hindered children's ability to use the system. In Visual StoryCoder, we aim to improve user system understanding for independent usage. Second, StoryCoder enforced fixed user flows and structures that introduce computing concepts without directly occupying children with computing practices, like decomposition and abstraction. With our multimodal approach, we aim to more actively engage learners with these computing practices, encouraging them to create high-quality, structured programs. Finally, StoryCoder asks children to plan their story around a set of predetermined options and constraints, limiting the possibilities of what a story could be about. In Visual StoryCoder, we aim to remove such constraints to better support the creation of personally meaningful projects. This multimodal extension of the StoryCoder system is aided by Flo the Fish, an instructional voice agent in the top left. This child has completed the planning process, so let's watch her make her first chapter.
I'm excited to hear your story about
It's about a basketball player
at
a basketball court.
Hit the check mark to get started. Awesome. Our story will have at least 3 chapters, a beginning, a middle, and an end. To get started, drag a dark green chapter block into our workspace. Just like in books, our chapters will hold pages. Pages are where we'll add words and pictures to our story. We can add pages to a chapter with a page block. Great. Every page should have both words and pictures. Tap on that page to start editing.
Oh.
In the beginning, we talk about the star and the location of the story. Can you tell me the beginning of your story?
This is about a...
Awesome. Now let's draw a picture for this page of your story. You can drag stamps of the star, location, and problem into the picture for this page, or you can use the toggle to switch to draw mode. Thanks for telling me about the beginning of your story. When you're done with the beginning, tap on the smiley face on this chapter and save it by choosing an emoji. Now that your chapter is saved, we can add it to your story. Your story is at the bottom of the screen. Tap the plus button to add a chapter to the story and select the emoji for the beginning chapter.
Through this interface, a learner specifically engages with abstraction and decomposition by modeling their program as a story and by breaking that story apart into chapters and chapters into pages. By defining chapters with emojis and then including those chapters in the main story, they're engaging in activities akin to defining functions and using function calls in code. Once a child has told their full story, they can engage with loops, events, and variables. For example, they can turn the stamps of the star, location, and problem into variables and change them out for new drawings.
A variable is a thing that can change, but we can only change one thing for another of the same type. We can make the picture stamps in your story into variables. Now can you draw a new picture of the location? Cool, now you're using a variable in your story. We have changed out the stamp anytime you used it in your story pictures.
And we can see that change then manifest in the story pictures wherever she used that location stamp. We conducted a between subjects evaluation of this system with 24 children aged 6 to 8. Half of these children used the Visual StoryCoder system, and half used Scratch Junior, a leading block-based programming app. We ran 6 first graders and 6 second graders in each condition, and none of the children had any prior instruction in computer science. Each child participated in 2 60-minute sessions over Zoom on 2 consecutive days. On the first day, the child played with the app for up to 30 minutes without any support or help from the experimenter. On the second day of testing, the experimenter first explained 4 key concepts in the app. Then the child had another 30 minutes to create a brand new project, and this time they were permitted to ask questions to the experimenter as they worked. Before going further, I want to lend context to this comparison. In Visual StoryCoder, children program stories using chapter and page blocks, while the agent provides just-in-time instruction. In Scratch Junior, children program animations by controlling the motion of characters using code blocks, like those you see here. This app has a tutorial video, which all participants in this condition watched at the start of session 1, but otherwise has little built-in instructional support. And through this comparison, we sought to answer 3 key research questions that related to our overarching objectives in supporting at-home learning through built-in instruction and emphasis on computing practices. We ask, how do built-in voice-based instruction and experimenter instruction affect the degree of system understanding among at-home users? How do built-in voice-based instruction and scaffolding around computing practices affect the quality of code produced by child users? And how do these systems support the creation of personally meaningful projects to drive user engagement? Today, I'll focus on system understanding and code quality. To answer these questions, we look at 2 quantitative metrics and 2 qualitative metrics. First, we looked at the degree of understanding children had of key aspects of the system, scored from a rubric based on a post-session quiz. Next, we quantified the quality of the code artifacts children produced based on an existing rubric for scoring Scratch Junior projects. We created a direct mapping adaptation of that rubric for Visual StoryCoder. We also conducted a qualitative analysis of data collected from experimenter observations during gameplay, and an artifact-based interview at the end of each session, in which we asked children about the projects they made. Looking at our data, we see an unsurprising significant effect of system understanding by session. Here and on all graphs, error bars show a 95% confidence interval. As you see here, we see an increase in system understanding in the second session after children have familiarized themselves with the app and received instruction. Interestingly, though, there's also a significant interaction between app and session. We see that children using Scratch Junior had a larger increase in understanding after receiving instruction, whereas this was not so much the case with Visual StoryCoder, where the change in system understanding after instruction was much smaller. We interpret this as support for the ability of built-in instruction to teach the child about the system in Visual StoryCoder, whereas Scratch Junior really benefits from the support of an educator. Looking next at code quality, we see that average code quality among children using Visual StoryCoder is higher than among those using Scratch Junior, but not to a statistically significant degree when aggregated across sessions. However, we see a great deal of variance in code quality in session 1, where children using Scratch Junior may not have touched the code blocks at all, or may have dragged every possible Scratch block into their project without knowing what they did. Also in session 1, multiple children using Visual StoryCoder didn't get through the full user flow of the app in the allotted time, meaning they didn't have an opportunity to engage with loops, events, or variables. As a follow-up, if we look only to session 2, where students have had an opportunity to familiarize themselves with the app and what it can do, we find that students using Visual StoryCoder do create statistically higher quality stories than those using Scratch Junior. We attribute some of this difference in code quality to the app's scaffolding around planning, a key computing practice. Qualitatively, we find that by and large, children using Visual StoryCoder talk about how they need to plan their story in order to tell it, whereas children using Scratch Junior talked about making up their story as they went along. For instance, when asked about how they got their idea for their project, a 6-year-old using Visual StoryCoder reported that it was important for me to have a plan, whereas a 7-year-old using Scratch Junior said, I technically made it up as I went. We view these differences in reported planning behavior as further evidence for the way that Visual StoryCoder scaffolding directly supports children's planning processes. Overall, with Visual StoryCoder, we demonstrate how multimodal interfaces with built-in instruction help learners better apply computational thinking practices.